Morning. Let's start today's session. Last class we have studied analysis of AC through pure resistive, inductive and capacitive circuit. But over here we are going to study the combination of RL, RC and RLC. So before studying this, we should know what is a J operator stands for. So it is nothing but it rotates a phasor anticlockwise by exactly 90 degree. Rotate J operator or rotate a vector a phasor exactly 90 degree in anti-clockwise direction. So mathematically J is equal to root of minus 1. Okay. So I will tell you what is the concept of phasor and waveform. So this is my voltage vector V, right? And corresponding phasor will be like this. So if I rotate this, right now this projection is 0. If I rotate it to this point, I'll get maximum value. And if I rotate to this direction, I will get 0. And if I rotate in the negative direction, I'll get negative maximum, like that. That is my phasor. And if I multiply V by J, it is actually leading by an angle 90 degree. This is my 90 degree. This is my VJ. Now how it looks like in the waveform? It will be leading. This is 0 degree now. This is again 90 degree leading case. So this is my waveform which I am going to obtain. So leading condition. So phasor if multiplied, so this is how it looks like. So I could say Vj is leading V by an angle 90 degree, or I would say I is lagging Vj by 90 degree. So now let's see our example, multiplying it many times. So first step I'm multiplying V by 1, so V I'll get. Second case, first multiplication of J, so I'll get J itself. And then the third point I am having Vj into J, so J square is minus 1. We know J square equal to minus 1, so equal to minus V. Then this minus V into J is actually we are doing, so that is a fourth step, and I will get minus Vj. Okay, so this is my vector. So first multiplication of J like this, 90 again and 90, again and 90, like this. See, this vector, this blue vector is represented in the waveform by this. This is my blue vector, normal sinusoidal waveform. And as I've mentioned, if we multiply it by J, I would get Vj, right? So this is my Vj, so leading by 90 degree. This is my Vj, looks like red one. Then minus V is this green one, right? This is my minus V. See, V is blue line, minus V is negative of V. So it's inverted in nature compared to V. Then this waveform, this purple one is minus Vj. See, this is Vj. So corresponding to Vj, minus Vj is inverted nature. And if I again multiply minus Vj with a j, I will get j square is minus 1, I will get plus v itself. This is the phasor operation or rotation using j operator. Clear? Let's see AC through RL circuit. The analysis is easier, similar to the earlier steps. All the analysis are going on in the same manner. So this is my AC supply V equal to Vm sin omega t. I have used a resistance and inductor combination, and this is the current I through it. And one advantage is that I is same through R and L. Why? Because both are series in nature. So V is Vm sin omega t, supply voltage. So if I am using a pure R circuit, my current will be equal to Im into sine of omega t. And if I am using a pure L circuit, my equation is I equal to Im into sine of omega t minus 90 degree. That is, current is lagging by an angle 90 degree, right? Now, instead of pure R and pure L, I am using a combination of R and L. So, this phi I will be using instead of this equation. So, phi is an angle which varies from 0 to 90 degree. It is neither 0 and neither 90. it is between say 1 degree to 89 degree, I would say. So I in RL circuit will be equal to Im sine omega t minus phi, where phi is an angle between 0 to 90, less than or less not equal to less than phi, less than 90. So this is the waveform. Okay, so as usual, our this is our voltage waveform. Here we kept voltages. We can keep anything as reference, either current or voltage. For analysis or further analysis, we keep current as reference. I'll tell you later. So this is voltage, and with an angle phi, I have to draw I, such that there will be a phase difference between V and I. So this is my current waveform. Clear? Let's see power in RL circuit. So we power is equal to V into I. So V is Vm sin omega t, I equal to Im sin omega t minus phi. So power is equal to V into I. Instantaneous power, that is Vm sin omega t into Im sin omega t minus phi, right? We know one mathematical formula, that is 2 sine alpha sine beta will be equal to 1 by 2 into cos alpha minus beta minus cos alpha plus beta. So it's here we have sine omega t sine alpha into sine beta. This is my alpha, this would be my beta. So what is alpha minus beta? I'll get plus phi, cos plus phi, and minus cos alpha plus beta. So 2 sine omega 2 omega t minus 5, the whole thing divided by 2. There is no division by 2, it's actually 2 times. So then P equal to Vm Im by 2 cos phi, this is final equation, minus Vm Im by 2 cos 2 omega t minus phi. That will be the power equation I have to use. Now let's see how this waveform has been drawn. So this is my voltage waveform, this blue one, and this is my current waveform, which is at an angle phi. This much angle is phi, I would say. Then first we have to draw this voltage and current. Then at points where either voltage or current is zero, just put a marking to draw the power waveform. So this is where voltage is zero, here current is zero, here voltage is zero, here current is zero. So like that, here again voltage is zero. So between these 0 point we'll be having a curve. Let's see the polarity. This is positive, this is negative, so this will be negative. Over here both these things are positive and having a higher value, so I'll get this power waveform. Then over here this voltage is negative, current is positive, so I'll get a negative. Over here both are negative, so I'll get a positive. This is the power waveform. So we'll have an average value of power somewhere over here. See the phi is where this is your 90 degree, right? Corresponding to 90 degree, your phi is very small. That means this resistive nature of the circuit, this example circuit is more higher compared to L. If you're having more inductive nature, this current waveform would have started somewhere over here. Clear? Next, let's go to another important points, right? So RL circuit voltage waveform. So this is very important voltage wave phasor diagram. I'll tell you how it works. So since we are having a series circuit, see we are having a series circuit like this, inductor and a resistor. Let the inductor voltage be VL, let the resistance voltage be VR, let V be the supply voltage, then I be the current away, right? So in this circuit the voltage is different because VL and VR will be different. So I have to take my current as my reference because current is same in a series circuit. With respect to current, VR and I are in phase. So this is in phase. VR is in phase. Now with respect to I, this VL is leading because inductor circuit the current is lagging a voltage by an angle 90 degree. That is why I could write this VL is leading. Now I have got VL as well as VR. Also we know that supply voltage is equal to inductor voltage with phasor plus resistive voltage phasor. So that will be your supply voltage. So this is your effective voltage V, and this will be the phase angle phi. Clear? So resultant voltage, this is same figure I am drawing. Resultant voltage V, this is I, this is drop across resistance VR, this drop across inductance VL, and this is phi. So V is equal to root of VR square plus VL square. Also I equal to cap total voltage by Z. Again, from this equations I am going to obtain another important section which is known as impedance triangle. So what is VR? I can write small I into capital R. Again, what is VL? I can write I into XL is inductive impedance. And what is V? I can write I into Z. So I'm taking only the impedances. I'm taking only the impedances separately, and I'm drawing another triangle such that this will be my R, this will be my XL, and this will be my Z, and this will be my phi. This triangle is known as impedance triangle. So how can I write? Z will be equal to R plus, if I have XL over here I have to write plus XL only, but now XL is not like this. XL is right now in a position which is rotated to an angle 90 degree, so it should be like J into XL. Instead of simply XL you have to write J into XL. So Z will be equal to R plus JXL, and tan phi is equal to JXL. This is A plus B now, A plus JB, right? So theta will be equal to tan inverse B by A, right? So similarly XL by R. Phi is an angle between 0 to 90 as explained earlier.